All right, number 2 is to place formal charges, and that means what that means is I haven't put the formal charges in. So you've got to figure out any atoms that have a formal charge, and then you need to draw a more stable resonance structure for the molecule that's shown. Okay, so go around here. You can do this you should get to where you can do this pretty quickly. Hydrogens all have one bond, they're neutral. That oxygen has 2 bonds and 2 lone pairs, so it's got to be neutral. Carbon's got 4 bonds, that carbon, 5 of the carbons have 4 bonds. A carbon with 4 bonds, neutral. So, for example, on this carbon, it's got 1 bond to the H, it's a bond to that carbon, 2 bonds to that carbon, that's 4. The one atom on the board that doesn't have 4 bonds is the carbon shown right here that I'm pointing to in red. Okay, so it's got a bond to H, bond to carbon, a bond to carbon, and then a lone pair. You can recognize that, or you can do the math. So 4 valence electrons minus half of 6 electrons, right? 2, 4, 6 shared electrons, so half of those. A lone pair is 2. That's minus 1. So the one formal charge on the board is a negative charge on the carbon that has the lone pair. And again, you should get to where you can just look at it and say, carbon's got 3 bonds and a lone pair, that thing is negatively charged. So then what about a resonance structure? So again, for a resonance structure, can't break connectivity. Okay, so this basically means you can't break a sigma bond. Right, this H can't move anywhere, the oxygen can't move anywhere. All you can move, so only change electrons. So electrons, if you think about an electron in a molecule, the electrons are either going to be lone pairs, you've got 3 lone pairs on the board, or they're going to be bonds. Bonds are electrons, shared electrons. The other thing, and it's kind of implied, if you can only move electrons, you can also move charge. So positive charge can move, negative charge can move. That could be, so instead of moving electrons, you can move a vacant orbital. And then the third thing, since we can only move electrons, the overall charge must not change. All right, these are the basic rules of resonance you would have learned, Chem 111, high school AP, chapters 1 and 2. So don't change the connectivity. Basically, when we draw this resonance structure, rule 1 tells us we can do this. All right, that's how all the atoms are connected. The sigma bond structure of the original molecule is reflected in this structure down here. That's not the resonance structure. We have to put in some more electrons, but that's part of it. Or that's the basic connectivity. Go down to number 3. Overall charge on this top molecule. Every atom is neutral except for one, which is negatively charged. So the overall charge is minus 1. Okay? So the overall charge on the bottom is going to have to be minus 1. All right, so now you have to figure out where you're going to put the electrons. And I'm going to show in a green arrow how you can do this. You've seen the curved arrow. We can use this lone pair to make a pi bond there. That carbon can't have 5 bonds, okay? I'm going to say this again. I know it sounds obvious, but I'll show something in a minute. This carbon cannot have 5 bonds. So if we make a new bond here, then this carbon all of a sudden has too many bonds. We have to move these electrons up. And so then the structure you get, okay, so this double bond stays the same, that double bond stays the same. This arrow basically means the lone pair goes here, makes a double bond. We started out with 2 lone pairs on this oxygen. We didn't do anything with them, so they stay there. And now the pi electrons in the carbon-oxygen double bond go up onto the oxygen. So we get a 3rd lone pair up there. Look at formal charges. Oxygen with 1 bond, 3 lone pairs is negatively charged. This carbon that was negative, so in the top structure, that carbon there was negative. Down here, it's now got 4 bonds, so it's neutral. The overall charge is reflected in that charge on the -1. Okay, so this is the answer. That is the answer. Good, that's on it. So, I'm going to show now, I'm going to erase this and show a couple of examples. Actually, I'm going to erase the rules over here. And I'll show a couple of examples of things people have done wrong. There's a big wrong, and then there's a not so big wrong. Okay. All right. So the answer that's not so bad, the one that's wrong that is not so bad, is this. Okay, that's not a bad answer. This structure, the third structure I've drawn, is in fact, so just a little resonance arrow to indicate resonance, but this third structure is in fact a resonance structure of the original. Okay, a lot of people drew that. Well, I say a lot of people. I've seen a few of them so far, and it's okay, except that it doesn't get that one. Sorry, I guess I should probably circle stable. I asked for a more stable resonance structure. So the structure here is a resonance structure, but it's not more stable than the original. The answer, the boxed in answer, is more stable because in all these structures we've got negative charge. Overall there's a -1 charge on the overall molecule. And that charge is delocalized, right? So we've drawn 3 resonance structures so far. Sometimes it's on a carbon, sometimes it's on another carbon, sometimes it's on the oxygen. There's actually a 4th resonance structure that's fairly important. See if you can draw that. You can come ask me about it, but it makes sense. It basically just moves the charge around the ring a little more. Of all these structures, only one of the structures has the negative charge on oxygen. Oxygen's the more electronegative atom in the molecule, and so putting the negative charge, the excess electrons, right? Electronegativity is an affinity for electrons. So this oxygen, which has an affinity for electrons, has the excess electrons. Okay, so this structure is more stable. Another thing that goes along with this benzene ring, I've drawn this in class a couple of times, and we're well short of being able to talk about it. But you might remember from Thursday, I talked about how this is flat, the bond geometries all work out. There's actually a molecular orbital reason as well, but benzene molecules are especially stable. All right, so this 6-membered ring with 3 double bonds, that's an unusually stable molecule. Like I said, we're not ready to talk about it, but you should stick that in the back of your head for later. So this is a much more stable resonance structure than the other 2. Like I said, this is a minor deduction because it is actually a resonance structure, and I want you to be able to draw actual resonance structures. That's good. So if you're gonna miss a question, draw me a more stable resonance structure. Well, drawing a resonance structure that's equally stable, okay, fine. That's not, you missed it, but you didn't miss it bad. Drawing a structure that's not a resonance structure or is not as stable, that's worse. And so that's where we get to this next one. And I have seen this, and I always do. And I'm not, if this is you, I am yelling at you, but I'm not angry with you. You're going to draw some bad structures in this course. But you need to learn now on sort of a 3-point question rather than later on a 20-point question. All right. So I have seen this. No, sorry, that would be pretty bad, wouldn't it? I have seen 4 of these so far, and like I said, I'm not halfway through. Okay, so this is basically move these 2 electrons here. This is our original structure in the upper left. Move the 2 lone pair electrons on carbon there and make a pi bond. Make a pi bond. That's in fact what you do in the actual answer. But then people have left that, what am I trying to say? People have left the carbon-oxygen double bond, right? That carbon now has 5 bonds. It's called a pentavalent carbon. It's wrong. It's always wrong. It's always going to be wrong. Moreover, The people who've done this so far have not shown any charge, so they've correctly identified a negative charge on the original structure, but then they've not kept a negative charge in the resonance structure. That's always going to happen. If you're drawing a resonance structure, the charge can't change. All right, you're not changing connectivity. You're not changing. The two resonance structures are just different ways of representing the same molecule, so the overall charge can't change. All right, so this is a really bad structure. If you got this one, look at it. Consider what your thought process was. If you really thought that was the right answer, it's a quiz and you're trying to get out and you got class after my class and you want to get lunch, whatever. If you meant to draw this and you just sort of whipped that thing in there and forgot to change the double bond, okay, fine. Like I said, you're going to screw things up. I'm going to screw things up. People screw things up. But if you really thought this was the right answer, you can't figure out why it's not the right answer, you want to come talk to me pretty quick. You need to get that straight. All right, that's number 2.